All right. Hello, everybody. Welcome to the class. This is the Statistical Foundation on Reinforcement Learning. Today is our lecture 10. So we are hoping to finish the chapter on strategic exploration. Yeah, at least to more or less finish it. So maybe in the next lecture, I'll still talk a little bit about exploration, but yeah, we're getting to the end of this section of the course. Let's get the lecture started. So far in the sequence of lectures, we've talked about how we can choose a sequence of actions to balance exploration and exploitation. We started with a bandit setting when there are no dynamics and all we have to choose are from a pool of actions. And then the finite action setting was extended to the tabular Markov decision processes with a finite number of state and action. And we derived an algorithm called upper confidence bound value iteration that essentially keeps collecting information, estimating the model, and then use the estimated model together with a slightly larger reward with an additional exploration bonus that added to the reward, and then basically run value iteration on that optimistic version of the Markov decision processes. And that gives us a valid regret bound that has a right scaling in terms of number of episodes that we take. And in the last lecture, we focused on the analysis of the regret for this UCB VI algorithm, which involves three main steps. First of all, we establish the concentration over the entire execution of the algorithm. For all possible variations, we show that the expected value is close to we show that the average is close to its mean in our estimate of the transition probabilities. And then based on that, we can come up with a set of so-called exploration bonuses, and together with a few other tricks that we've learned in a bandit setting, and we were able to complete the proof. Okay, so today we're gonna talk about an extension of the linear bandit setting, and we'll be talking about a new model called linear MDPs, which is a powerful model that allows us to handle, say, an exponentially large number of states, while only depends on certain feature representation of the states. So why do we care about this problem, right? Yeah, basically we'll be following the same model, right? The reason why we care about this problem is that the state space of these Markov decision processes and action spaces, they're typically very large. Sometimes they are say in a game of chess or Go, this state and actions, they are easily 10 to the power of hundreds. That makes it intractable to visit every possible state action pairs and explore the possibilities in these games. On the other hand, the states are not completely independent to each other. There are information that we can learn from one state that could generalize to other states that share similar features. Okay, so the formal setup is identical to the setting that we considered in the last lecture, except that the parameterization and the specific choices of state action and transition kernels, say they are not different. We still have we still have the policy that depends only on the time step for every individual policy. So when we talk about policy, we talk about the policy at every time indexed by h. So for each pi of h, this is a mapping from state to action. Yeah, more generally, you can define the probability distribution on action for stochastic policies. But so far, the exploration and the algorithm that we've been dealing with only deal with deterministic policies, because we know that the optimal policies are at least there exists the optimal policies that is deterministic. Yeah. Yeah. At this point, I think it's for those who haven't checked the Piazza post. It's worth mentioning that one of the homework questions that asks you to derive the Bellman equation for variances. So that expression is only true for deterministic policies. So many of you might have run into issues trying to prove that. So I inherited this question from Wen Sun and Sham Kakade. Like they didn't say it explicitly. But I checked that it only applies to the deterministic policy, and for more general stochastic policy, there's additional term, or alternatively, you have to replace that V function with Q function, right? So yeah, for those who know what I'm talking about, then you know what I'm talking about, and for others, then if you run into trouble proving that part of the homework one, then maybe it's worthwhile like going back there with that in mind. Yeah, with this additional assumption that the policies are deterministic. Okay, so the regret, the natural performance measure for any agent is the expected value of the difference between the oracle's performance, who keeps playing the optimal policy, versus the value of the policy that this agent come up with at every epoch k. Okay, and this V star, since we're starting with S0, is defined as V0 S0 pi star, and V pi k is defined as V0 S0 and following pi k throughout. Okay, these are definitions. Yeah, so more on like why do we care about such a linear function approximation? Why do we care about a linear representation of the state and maybe state action pairs? So we've talked about this example. So if we are in a completely tabular setting, so every one of these states, all these three states in the Pacman environment, they're completely different, and the agent are not supposed to know any additional information that connects this one state to another, even though like these are actually very similar, that the Pacman is trapped in a tunnel in between two ghosts. And we know that this state is something that has a very very low value. So the featurized representation of the state say that if we represent the states as a list of extracted feature values, say F1 could be the distance from the closest ghost, right? The second one could be like whether there is any places suppose the ghost is not moving, whether you can escape this, right? And you can come up with all sort of features that you can efficiently compute based on the deterministic based on the actual state itself. That is like very informative on the value of the game. And similarly, you can do that for state action pairs, and that helps you to design algorithms that generalize from one state to another, and design an agent that learns significantly more quickly than a tabular agent that treats every state as something that's entirely new. Okay, and how do we formalize this this argument, and how do we come up with a mathematical model so that we can say analyze the regrets of this problem setup? And what are the assumptions? What are the kind of weakest assumptions that we need to make in order to make this a well-defined problem? Okay, so I guess the weakest possible assumption that we can think of is say maybe like we only want to assume that that we don't want to assume that this Q star function is actually linear. Say given a feature. So maybe Q star function is well approximated by a linear function. So a linear function of the feature. And nothing is known about other policies, but only the Q star function. If that is the case, then we know that the right policy to take like could be so based on this this conversion from, so remember that we have proven this lemma, which says that suppose you can get an f function such that f function and Q star function in terms of L infinity norm is smaller than epsilon, and this implies that the policy arg max of f implies that this policy is also nearly optimal, right? So this policy, the value of this policy is smaller than epsilon over 1 minus gamma in the infinite horizon case. In the finite horizon case, you have a version of this amplification lemma, right? So if we know that this is approximately linear, then maybe we can get a good solution already. And slightly stronger, maybe we can assume that this Q pi function for all possible policies is approximately linear. So this will be a stronger assumption than the basic assumption that we are willing to make. On the other hand, like it has been proven that these assumptions are not sufficiently strong to rule out some really hard cases. It has been proven that if these are the only assumptions that you are willing to make, then it requires you to interact with the environment for exponentially many. So there's this lower bound that says that it takes e to the power of h episodes before you learn a policy that's approximately optimal. Okay, so having this exponential dependence certifies that these assumptions are not good assumptions to study theoretically, because there's this impossibility results. So what if we make additional assumptions by saying that well, the Q star function is exactly linear, right? So by saying that, I mean we are given this feature vector phi of SA such that Q star of SA is equal to some theta star parameter transpose theta of SA, right? So this is a very strong assumption because in practice we have no idea like whether this is true. On the other hand, even up to this point, like only knowing that the Q star is exactly linear is not sufficient for us to learn. It's insufficient for us to like, at least it hasn't been proven that this is sufficient for you to learn optimal policy with a polynomial number of episodes, with a polynomial number of samples. Even in the generative model setting, this remains an open problem. And even stronger assumption is that we can assume that for all policies that this Q pi function is exactly linear. And this is an even stronger assumption than what we can make about the Q star function being exactly linear. And in this case, it is known that if you assume a generative model setting, or alternatively, if you assume the state transitions are deterministic, so in these two cases, you can have polynomial sample complexity in learning the optimal policy. And in the full reinforcement learning setting, so even for this problem, it remains an open problem of how to address this, right? So in this lecture, we'll be working with a model that is even stronger than the last one, but now this setting is more well understood. And we know that polynomial sample complexity is possible in all the parameters, and we also know that there are algorithms that we can derive that achieves the information theoretic limit that in some sense solves the problem optimally. Okay, so these are the family of problems called linear MDPs. So let me illustrate like what are the additional things. So these are like episodic MDPs. So let me illustrate that what the additional assumptions that we need to make to specify the linear MDP. So basically it says that we are given access to this feature map, right? So this feature map that maps any state action pairs to some vectors in a d-dimensional Euclidean space. And then the reward function is linear, and in addition, the transition kernel is also linear. Okay, so there are some unknown parameters, theta h and mu h star, that gives us these probability distributions and this expected reward. Okay, like this is straightforward. This is so let me maybe draw the size of this vector. So this is the same as the theta h star transpose phi of SA, right? So it gives you a scalar, and you have this kind of matrix vector multiplication. And on the other hand, the transition kernels. So this is slightly more interesting. So what we are assuming is that so notice that like for now let's assume that the state and action they are finite, but they are a like very large number, right? So we know that the transition kernel is has a dimensionality of S times SA. Right, we know that this is a huge matrix that is needed to describe this transition kernel, and of course when both S when S is a continuous state, then this is an operator, right? That maps one function to another. So what this assumption is assuming is really that this matrix is rank D. Right, so let me show you why that is the case. So what is the dimensionality for this parameter? So the parameter has a dimensionality of S multiplied by D, right? And this one is a d-dimensional vector, right? So what this is saying is that if you count the number of parameters that's needed to describe the model, is actually astronomically large. So the kind of the number of parameters is I guess D from this theta h star, everything multiplied by h plus S times D, right? So since there is a like size of the state space inside, so we're considering the very large Markov decision processes when the state space can be exponentially large, then we cannot actually hope to estimate the entire model accurately with a very small number of samples, right? So that what makes this setting. So even though it is a very strong assumption, it makes it somewhat more interesting because the number of parameters to describe this Markov decision processes is actually quite large. And though we still want to derive like polynomial sample complexity and regret bound that it doesn't depend on the size of the state space at all. Okay. So it is a low rank assumption because if we enumerate over all S and A, and this becomes like a dictionary matrix that's given by SA and that's given by SA and D by SA, right? So this is saying that the transition kernel P H dot and this factorizes into the product of two matrices with an interior rank being D, right? Therefore, this is an assumption on the low dimensional structure of this transition kernel. Okay, so let's like try to formulate the tabular Markov decision tree processes as a special case of as linear MDPs, right? Can I get one of you guys to tell me like what I should choose this dimensionality D to be, what I should choose this feature map to be for this to recover the standard tabular Markov decision processes? So anyone? Yeah, you could type into the chat or just unmute yourself and speak up. Now again, in tabular MDP, this is just this is we want to, S and A are finite, and we want to represent this without loss of generality. Anyone? Is a definition of a linear MDP clear? Yeah, there was a question asking about the. So are you asking about the low rank part of the large MDP or transition kernel? Yeah. So basically like this assumption says that this is this mu star, right? This is mu h star, and what is this? Every individual column of this is that you enumerate all the SA pair, and then you put in this SA S1 A1. This is phi of S2 A2, and then you enumerate everything. Therefore, this is a short and fat matrix, and the and this one, this parameter, like is a tall and thin matrix, and if a matrix factorizes into the product of two matrices, then the rank of the matrix is upper bounded by the smallest dimension in the factorization, right? So in other words, every column of this matrix can be represented as a linear combination of D basis functions. Therefore, it has a like low rank structure. Is that clear? Okay, now let's get to this. So can anyone tell me like how I can write tabular Markov decision processes as linear MDPs? Yeah, this should be pretty straightforward. Anyone?
Well, maybe we can actually choose this phi of. So let me start with our reward function.
Mm-hmm.
So maybe phi of SA we can actually use a one-hot encoding of dimension SA, and theta h star we can actually use the reward itself of dimension SA.
Okay, yeah, excellent. So the D is a product of the cardinality of S and A, and this phi function basically is a one hot indicator, right? So one hot indicator. So that's a standard basis, S and A, right? So this gives you one if the input if input is SA and 0 otherwise, right? So that's a feature vector, and similarly the same feature vector got applied here. Then this is really selecting from the full matrix of S times SA, right? So this is a conditional probability matrix, and if this multiply with one hot representation, then what it does is that what it does is that it selects a particular column, right? Which gives us the conditional probability distribution. Okay, yeah, the feature map phi SA to be one yeah, to be this long vector of the size as a, and then this location is where this index of this particular pair of SA, right? So this particular location is 1, and everything else are zeros, right? So that's how you recover the tabular Markov decision processes using a linear MDPs. So in this sense, the linear Markov decision processes are strictly more general than the tabular MDPs. Okay, so the linear MDPs. So back to the sequence of assumptions, so the hierarchies of possible assumptions that we could make. So linear MDPs imply that the Q function for any policies is also linear, right? So let's see why that's the case by starting with the optimal Q function. So we can do that by simply write down the Bellman optimality equation, right? By writing down the Bellman equation, which says that the Q star of H, say SA, so this is equal to Q. This is equal to R SA plus the transition kernel SA like transition kernel and this one inner product with the V function. Yeah, with the V function itself, right? So by the linear MDP assumption, this is a linear function. So the reward is a linear function. So we have theta star, right? And then we also know that this transition kernel is a linear function. So we can write this as we can write this as mu times phi of SA transpose VH plus 1 star, right? So and then we can group all these features together. We can group this phi of SA together, and then put everything else into this theta star. I guess plus mu H star mu star transpose V star H plus 1 dot transpose of phi of SA, right? And then this is equal to some parameter. This is equal to some parameter transpose phi of SA. Some parameter that depends on the value function, right? So notice that this argument also works if we replace this with any generic function mapping from state to a real value, right? So the same argument would follow through. Therefore, we can substitute this f to be this f to be the value of pi, right? The value of pi for any policy, and this shows that the Q function for any policy pi is linear. Yeah, it doesn't have to be pi. This f can be anything else that you plug in here, and the same argument would work through. And you will get the corresponding value function in this Bellman backup is linear in the Fisher representation. All right, so this is indeed a stronger assumption than the weakest assumption, than the strongest assumption that we wrote at the beginning of the lecture, right? Because it implies that for all policy pi and the value functions are exactly linear with respect to some unknown parameters. Okay, so now let's talk about the algorithms in linear MDPs. So we'll start by revisiting the algorithms in the linear bandits case called UCB, right? So I hope you still remember how this algorithm works. The idea is that you first start by, so at every time point t, you estimate the unknown parameter of the model, theta, and you estimate the unknown parameter like mu star with mu hat of t by solving a ridge regression. So it is a linear regression together with the regularization term. So in this case, the label are the rewards because these are the linear band this case, and the reward are not known and they're stochastic, and so you need to estimate it. Then once you estimate this theta, this is mu hat, you can construct a confidence set that is an ellipsoid based on the actions that you have taken so far by constructing this this sigma matrix. And then you call this an ellipsoid, and by choosing this beta t parameter carefully, you can ensure that the true parameter is trapped within this ellipsoid with high probability. So so you know that this mu star is somewhere inside this ellipsoid, right? And then in order to get optimism, you consider the best possible case of where this theta star is within this ball, and then choose your action according to that optimistic view of the world, and that gives you the next action to take, right? So that's the Lin UCB, and we've shown that this gives you the nearly optimal regret of square root of t. Okay, and the I guess the upper confidence bound algorithm for linear MDPs is a combination of the Lin UCB algorithm and the UCB value iteration algorithm for the tabular MDP that we talked about in the last lecture. So similar to the previous Lin UCB, so in every round we run the same ridge regression for estimating the model. Right? So we run the same ridge regression for estimating the unknown parameter of the model. So in this case, the unknown parameter of this model is this the parameter. The parameter of the model is only this mu star, and mu star again is something that's s times d. Right. So notice that we assume that theta star is known. Like we don't have to assume this is known, but from homework 1, it is clear that the reward part of the problem is like a solvable problem. That's something that's more easily addressed. So for now we assume that the reward is known, while the transition kernel being described by this like really high dimensional parameter vector, right? Still, so we can hypothetically like solve this by solving a ridge regression. So in this case, the feature vector is a state and action that you run into at episode I and step H, and then we know that this is a linear function. We know that this is equal to the with the right mu, this is equal to the probability of this is equal to the probability of SH and AH, right? And what we get is an unbiased estimator of this vector, right? So this vector is in R of S. What we get is an unbiased estimator of this with this one hot representation of SH plus 1I. So this is our label, and this is our feature. Right, so it's a standard supervised learning problem with square laws, so a linear regression problem, and we're adding this additional regularization term. And what is Frobenius norm? How many of you know what Frobenius norm is? So, but you do know like what Euclidean norm is, right? So Frobenius norm take a matrix. So in this case, the parameter is a matrix, and this is equal to just a vectorized input and then Euclidean norm. Basically, you square every coordinate and add everything up, and then take square root. Okay, so this vector is also in R to the S, and this is a vector that that is one at the particular observed state, and zero elsewhere, and by the distribution how this is generated, we know that the expected value of delta of S I is equal to P SHI AI, right? So in expectation, this is a right number that's supposedly given to you by a linear function of mu star inner product with with a feature vector, right? So it's a valid choice, and since these are just quadratic minimization problem, and you can take the gradient and then set the gradient to 0, and then you can write this in the closed form. You can write the ridge regression estimate in the closed form solution with this formula where we define this eta this lambda, this capital lambda matrix to be the summation of I from 1 to n minus 1 phi S H I A H I phi S H I A H I transpose plus this additional regularization term I times identity. Okay, so all these are like very similar to that of the linear bandits. So this is the same. So the regularized the Hessian matrix of the objective function, which stays a constant regardless of what input mu is that you enter the objective function. And then like we should define an exploration bonuses in order to run the UCB value iteration. So recall in the UCB value iteration, we in optimistic value iteration, we go from the last step by and then keep applying the Bellman backup, the Bellman equation, and that in every iteration, you get the corresponding policy for that iteration, and you do that all the way to h equals to 0. So the difference and what makes it optimistic is that you're adding this additional term to the reward. So in UCB VI for linear MDPs, this is a family of reward that we consider. There's some parameter beta that we will determine later. And then and this is the in the linear UCB lecture we call this the width of the width of phi SA in the natural geometry, like measured by measured by this lambda matrix. Okay, so once you have this completely specifies the algorithm. We run optimistic value iterations, and then we can get the corresponding greedy policy that's given to us by that value iterations. So again, so this is how optimistic value iteration works. So we specify like a dummy case with a dummy value function at step h to be 0, and then we recursively construct the Q function estimate by this is the reward R of SA, right? This is our it should be indexed by h, but since we know this theta star, then everything is fine. So this is R, and well, this is exploration bonus. This is exploration bonus BH at step n S of A, and what is this? This is simply the probability distribution of the state transition based on our estimate. In the product with the estimated value function from the next from the subsequent step, right? So this is nothing but running Bellman equation based on our approximate model, and well, you can group these two together and write it in a slightly cleaner form. Okay, and once you have that, we can construct the next v star v hat function by taking the smaller of the max possible value of h and what is given to us by this optimistic value q value functions, right? So this is how we construct this v hat, and after that we can recursively call this and then deal with the step when h is equal to h minus 1. Right, so this is the same optimistic value iteration from the previous lecture, and as we do that, we can come up with the next policy to run as we back up from the last step using dynamic programming. Okay, the only difference is now that we substitute into our additional model assumption that these transition kernels are linear, and our estimate is also given by the estimated model parameter. Right, and the exploration bonus is also different. But other than that, it's the same old value iteration with an exploration bonus. Okay, so what this let's start with a theorem. So the result says that if you choose this beta parameter in the exploration bonuses with something that's proportional to HD, yeah, so everything else are logarithmic factors, depending on the boundedness of the space, dimensionality, and so on. But if you choose this beta parameter to be this quantity, you choose this regularization parameter of your ridge regression to be 1, then that implies a regret bound on the order of h squared square root of d cubed times n, where n is a number of the number of episodes. The number of episodes your agent play and interact with the environments and collect data. Okay, yeah. So there's actually one more thing that I wanted to talk about regarding the algorithm. So we've said that that we don't really want to have like polynomial dependence in the size of the state space, right? On the other hand, like if we're running this ridge regression, it appears that this estimator, this mu hat of nh, is in R of s times d, right? So it appears like we will have to somehow represent a exponentially large matrix, and that takes up all the memory. So what is the what is the saving grace here, right? So if you look at this, this is actually a sparse representation, right? So in order to calculate this, all you have to do is to keep track of this d by d matrix, and this use this new d-dimensional vector, and then keep track of the entire data that you observe. Right, so these are the sequence of data that you observe, and this is a one-hot representation, and this vector is sparse. So even though this vector is s-dimensional large, which can be exponentially large and possibly a continuous, like when s is a continuous variable, and this is infinitely long, all we have to do is to keep track of the data that we observed so far, right? Because of that, and this algorithm is a polynomial in everything. So we will see that we like all we actually need to do is to deal with inner product of this with all the other vectors that are that has the same length, right? And the evaluation of those inner product will require us to just stream through the data, which makes it space efficient, and it doesn't really violate our initial primitives that we want something that has polynomial runtime and also polynomial space complexity. Okay, so I hope the algorithm is clear. Okay, so that's the algorithm, and this is a regret bound. So let me sketch out the arguments to obtain such a regret bound. Okay, so the underlying idea of analyzing this algorithm is yeah. So Diraj asked a nice question. So we can we apply the same algorithm from the kernelized version as well? Yes. It requires some work. So the kernelized representation, the kernelized version like has a different infinity there. In the kernelized representation, this D is actually infinity, right? So you're dealing with functions and operators and so on. So in the primal representation, you still have to deal with this D by D matrix and this inverse, right? So in order to get the kernelized version of this algorithm to work, you have to apply kernel trick and then essentially represent only the kernel matrix rather than explicitly representing this D by D ellipsoid, right? So the whole argument would go through like with little changes in the kernelized version, but the concentration type of argument requires you to deal with the reproducing kernel Hilbert space, and then in the algorithm design, it requires you to use kernel trick and represent the same quantities in the dual space.
So are those results already present in the literature?
I'm not entirely sure, but I think so. So you should look at the AJKS textbook and look at the bibliographic notes towards the end of this chapter. Maybe there are some pointers there. Yeah, I think it has already been done with a kernelized version. But yeah, maybe it's worth looking into. Yeah, good question.
Thank you.
Okay, so let's sketch out the idea of the regret analysis. So in the regret, like we're still need to have the same kind of elements. We need concentration, basically showing that the randomness doesn't matter, and with a large number of samples, we get something that's close to the mean. And then we also need optimism. We need to show that this choice of exploration bonuses actually gives us the optimistic estimator, right? So we'll to just try like following the same kind of argument that we had for the regret analysis for the tabular MDP, and see where are those lemmas needed, and before we try like writing down like what exactly those lemma is. Okay, so we'll start by say analyzing the per episode regret. Right, so this will be very similar to the kind of regret analysis from the last lecture. This is what we want. We want to take the difference between the oracle's performance and your agent's performance, right? So in episode n, your agent plays policy pi n, and this is their expected cumulative reward. Okay, and by our definition, this is starting from S0, following the optimal policy, and starting from S0, following this particular policy pi n. And if we can prove optimism, which says that you get which says that your pi n is a argmax of a value that is larger than the actual like v0 star. Then you can upper bound this due to optimism by this estimated quantity together with the exploration bonus, right? So then this converts the problem into into something that's handled by the simulation lemma, right? So to recall in simulation lemma, so this is a version of the simulation lemma that also deals with this clipping at h. So remember this this clipping at h, which always makes it smaller, and therefore we can use the simulation lemma of the original thing that tries to upper bound this quantity. So by the simulation lemma, we can get this to be the running this policy pi n, and so recall that the first term is the difference of the reward, and since the reward is the same and we are just adding these exploration bonuses, and this the difference becomes only the exploration bonus. So this will be SH. So whenever I write these capital letters, I'm explicitly saying that they are random variables inside this expected value. So this is not made explicit in the textbook, but I figure this makes the proofs that easier to understand, and it's always a good idea to ask yourself whenever you see an expectation, what is random, and what are the random variables in the expression, right? So capitalizing all these random variables. So these are the state action pairs that you see by actually running this policy pi n. Plus, so in the from the simulation lemma, so you'll have the difference between the estimated estimated transition minus p h. So this is the actual transition, actual probability distribution of this transition. Wait. And this thing is got inner product with this estimated value function of the next step, h plus 1. This is n. Okay, so this is by the simulation lemma. And once we have this, we got to a point where like we remember that in the tabular MDP case, like we bound this by a Holder's inequality, and then we obtain an L1 norm error bound of this estimated transition kernel together with the trivial L infinity norm of this value. In this way, we can get away with not having to worry about the dependence between these two random variables. Okay, so here we cannot do it, and because if we use L1 norm, then the bound will depend on then the bound will depend on square root of s, which depends on something that's exponentially large. Okay, so this is where we need a lemma, lemma of uniform concentration. So which says that with probability 1 minus delta for all state action time step and also the index of the episode, then there's a function class f such that for all function within this function class f, so function class f contains the set of all possible value functions that this v hat function can be. P hat hn sa minus p sa h. So this thing inner product with f, right? So f is a f is a function that maps the state to a value. So in the vector representation, it is an s-dimensional vector. So this is smaller than beta phi s a lambda n h inverse. And well, this is our exploration bonus. Right. So like let's not worry about how do we prove this, but if we hat h plus 1 n is inside this function, then you can apply this high probability results by saying that with overwhelmingly large probability, then we can bound this quantity of interest by the right hand side, by the exploration bonus, right? So if we do that, then if we do that, then that implies that we can basically bound this by sum over h to 0 to h minus 1 expected value of pi n, and 2 times exploration bonuses sh ah. Okay, and then once we have that, what is it that we can do? So this lemma implies that with high probability v star minus v pi n, v pi n is smaller than yeah, let's like convert it into the random variables that we actually see from the exploration of the agent, since the last iteration actually is run by the agent to collect the data. So we can replace these random variables Sn and Sh and Ah that are generic with the actual data that we collect, right? So this is smaller than sum over h from 0 to h minus 1, 2 times b h n sh n and a h n, condition on the history that we've seen up to the n minus 1's episode. Okay, so why can we do this? Why can we replace? Why can we add this superscript n? That's because this shn and ahn are identically distributed as with the generic sh and ah by running that particular policy. That's because in this episode we actually have run this policy pi of n. Okay, so now the regret I guess the total regret basically requires us to take the expected value and then the summation from I from 0 to n minus 1 and v star minus v pi n. Right. This is where we can substitute this into the expression, and by consider the two cases. Right. In the first case, this is when this uniform convergence, uniform concentration bound is valid. So that happens with probability 1 minus delta. And the other case is when this uniform concentration actually fails, that happens with probability delta. So let's decompose this expectation into into two cases, and by adding this indicator. Indicator of the event not fail plus this the same event. This is I from 0 to n minus 1. V star minus v pi n indicator fail. Yeah, these two events complements each other, and then we can apply this this bound that we got. So in the case of the fail, we will get the sum from and sum also over h 0 to h 2b hn sh shi ahi all right, indicator not fail. and plus delta. So we'll just use a very crude and conservative worst case bound for the case when this fails. So this is smaller than the probability of some worst possible thing could happen. And notice that these are the differences between the value functions, and V star is optimal. Therefore, like the worst that this pi n can do is to keep getting like 0 reward and throughout, right? So this is smaller than n times h, because h is a upper bound of the cumulative reward that any like poor performing agent would incur. Okay, so it suffices to choose delta to be some small value. And now, how do we bound the first term? And by getting rid of this not fail, this is an indicator that's either 0 or 1, and the term that it got multiplied to is always non-negative based on our choice of this exploration bonuses. Therefore, we can simply drop this and write this down as an inequality, right? We can simply drop this without changing anything. All right, so let's move to the next page and then try bounding this term and see what are the things that we need. Okay, so let me first write it down. H from 0 to n from 0 to n minus 1, h from 0 to h minus 1, and we got the exploration bonus, bh of n, shn, ahn. All right. So so by our choices of these exploration bonuses, this is simply beta times h from 0 to. Yeah, I like this index I a lot better because that makes it harder to confuse between h and n. So let's stick to I. So by our choice of exploration bonuses, this will be just AH of I and this ellipsoid right. Yeah, I guess then. Oh boy. Yeah, these notations are driving me crazy. Better switch it to n to be, yeah, because we're using this to talk about the nth episode, and then sometimes we also need to iterate over I. So let's save I for other purposes. This is just a definition, right? This is just our definition of these exploration bonuses, and remember what we did typically, like in the tabular case. In the tabular case, what we've gotten here is like something that's similar to this with exploration bonuses, but in the tabular case, what we have is some term that's 1 over n as a pair, right? And then we can group all the SA together. We can group all the SA together and then exchange the order of summation, and that gives us the summation of 1 over square root of I from I to NH and SA. Right. So in the tabular case, these are what gives us a bound, and in order to get that, the idea that we applied is a Cauchy-Schwarz inequality, right? And we'll be applying Cauchy-Schwarz inequality here as well. So this is smaller than beta. Let's extract this summation over the horizon out first, and then apply the Cauchy-Schwarz inequality to this summation over n. So this will give us n and little n from -1. n inverse phi Sn sh of n ah of n. Right. So this is what we got, right? Remember that this should be something that's familiar to you, and this is the sum of the square width. Like you've seen this from the linear bandit lecture. So the similar lemma from the linear bandit lecture would be the information gain style of bound of this quantity. Yeah, this is where we need another lemma to just write it down. So for which says that for any such sequences of sh of n, ah of n, for any such sequence, yeah, we can obtain a bound that's independent to the choices of the algorithm. We can bound the sum of n, this is summation of this capital N term. Now we can bound this by first making it log 1 plus x, right? And then apply the algebra in the log, and eventually this can be bounded by something that's theta d log of n. Yeah, this is coming from replacing this with log determinants. So there are things that keep canceling with each other, and at the end you get this dimension dependence d, and then log of the number of episodes, right? Like for the sake of the analysis, let's take this and then substitute into this expression, and then what we'll get is the like and then what we'll get is so notice that beta, our choice of beta from the theorem is HD, right? So let's substitute the choice of beta here, and then there's a summation from the over h quantity. So that becomes the d times h square, right? And then inside the square root, you will have a square root of n, and together with this additional quantity, d log of n, right? So that gives us the h square d square root of d cube and n bound that was previously claimed here. Okay, so that's the general structure of the analysis of this regret. So what are the components that we used here? We use this optimism in order to get over the first step by replacing this unknown quantity v star with something that we can actually estimate, right? And then by simulation lemma, we can bound the differences between the optimistic estimated value of and the actual value. And that converts things into something that we're familiar with of the error in estimating the model, right? And since this error in this estimated model and the choices that you decide to run the policy will give you two correlated random variable, we need to somehow deal with this inner product. We need to somehow deal with this inner product in a slightly more complex way than simply collapsing this as if this value function is fixed and given. Then so we need to use a uniform convergence, and once we substitute the uniform convergence bound, and like notice that this exploration bonuses are explicitly chosen to be the quantity that makes this work, right? So that once you choose this, then this exploration bonus and the error that you get from the second term, they are on the same order. And then by adding up the per episode regret bound, and then we get an upper bound of the total cumulative regret after we take care of this failure event, right? So to take care of this failure event by this is the worst possible failure mode. And since we can choose this delta to be arbitrarily small, and this term can become negligible comparing to the rest of the terms, right? And it remains to bound the expected value of the summation of these exploration bonuses. So that requires our bonuses to be not too large, right? So we need to add just enough bonuses in order for this algorithm to behave optimistically, but we cannot be blindly optimistic. So the algorithm will choose something that's way suboptimal, right? And that like can be further bounded. And that can be further bounded through the information gain argument, which gives us which gives us only a term that depends on the dimension, but only depends logarithmically on the number of episodes, right? So I didn't actually prove anything here. I'm only sketching out the overall argument of the regret analysis, and the key complexity of the analysis is hidden in this uniform concentration analysis, in this optimism, and also in this information gain bound. And luckily for some of these, we've already seen the related argument from the simpler version of this model. So it becomes easier to digest in the later lecture today. Okay, so let me answer this question by Monzish, and then we'll go into our break. So the question is that should the limits of H in the second step, yeah, so sorry, I missed your note at the time I was presenting. So could you tell me which page is this?
This page itself.
Oh, so it is this page. So it's the second line here. Oh yeah. I think you're right. So this is the typo, summing from H from 0 to H minus 1. Yeah. All right. So so it remains for us to prove the uniform convergence, the optimism, and then also the information gain bound. Right. So we'll take 5 minutes break, and we'll resume at 2:20, and we'll come back to tackle these lemmas and tackle these hurdles. All right, see you folks at 2:20. All right. Welcome back to the lecture. 220. So let's resume the lecture and talk about the ideas behind some of these lemmas and how we can get optimism and how we can prove this concentration bound in the linear MDP case. So first of all, I'd like to highlight that the optimism and information gain bound, they are almost exactly the same as the bound from things that we have covered already. So the information gain bound requires this transformation into from x into, for small x, into log 1 plus x, and then that allows you to work out things inside the logarithm with a log determinant. And I'm gonna completely skip that, and you should read the lemma 7.12 in the AJKS book. Okay, so I'm gonna talk briefly about optimism, which will end up relying on the kind of bound, the same type of bound that we need for the uniform convergence. Okay, so let's first talk about optimism, and then I'll talk about the uniform convergence bound of that quantity p hat minus p multiplied with some f. So we want to bound this to be smaller than epsilon with probability 1 minus delta. So that's the kind of uniform convergence bound that I'm talking about. All right, so we'll start with optimism. So the argument for proving the optimism is still by the way. So what is it that we're trying to prove? We're trying to prove that the way the optimistic value iteration will give us this V0 hat, and then the corresponding policy that we get out of it is pi of n. So we want to show that this is for all possible s, this is larger than well, yeah, s0 and star, pi star. Yeah, so this is the optimism that we need and that we used in the first step of the regret analysis. Okay, so the idea is to go by induction. So we can first assume that V hat of n h plus 1 s is larger than V star of h plus 1 s. Right? Then we want to use this inductive hypothesis to show that this Q hat n h of SA is I guess minus the Q star h of SA is larger than 0. We want to show that this is larger than 0. Okay, and the same argument as before was to first apply the Bellman equation to both of these quantities, and then take the difference between the Bellman equations on the right hand side, and then let me write it out. So you will have this R S of A plus the exploration bonus phi of SA transpose lambda H inverse phi of SA, right? So this is your exploration bonus together with your state transition. So in the linear MDP, the state transition can be written as the phi of SA transpose your estimated model parameter mu H n transpose and V hat. So this is the what you get from the next step, right? So the corresponding value for Q star is the same. So minus R of SA. So these two got canceled. And minus phi of SA. So now you get this mu star of n. So this is a true parameter, right? So this is This is a true parameter, and inner product with this H+1. Okay, and we can lower bound this by simply replacing this VH+1 star with V hat H+1n, right? So this is by our inductive hypothesis. So we will have this exploration bonus. Plus phi of SA mu hat of n h minus mu star of n transpose with V hat H+1 n, right? This is by applying the inductive hypothesis, right? And in order to prove this, like what we really need to do is to choose this beta to be sufficiently large, right? So if we choose beta such that with high probability, so beta of this phi SA transpose is larger than phi SA transpose this error estimate, right? So if this is larger than that, then we've proven that this is optimistic, right? So this is the same argument, and this is essentially telling us that the choice of beta, the choice of this beta, and the choice of the function form of this exploration bonus is closely related to the kind of upper bound that we can get of this error term. Okay, so I hope that this explains that how the optimism is also related to how we can derive this kind of uniform convergence bound. So recall that the kind of uniform convergence bound that we need is super over f in some function class where we know that we hat n h+1 is inside this function class, right? If we can get an upper bound of yeah, absolute value. If we can get an upper bound of this quantity, with f, we can somehow bound this quantity, and then we can apply this to here, and it suffices to take the exploration bonuses to be whatever upper bound that we get here. Okay, so yeah, before proving the uniform convergence bound, let's start with pointwise convergence bound. So what is the difference between pointwise and uniform, right? So by pointwise, I mean that for every fixed f, right? So for every fixed f, right, we can just work only with the randomness of the data that construct this ridge regression estimator, and then we can construct some kind of bound there. Right, so that doesn't allow us to choose a data dependent choice of f, because then there will be optimization bias if we optimize it. If we maximize this quantity, then we'll pick up some of the errors, and we'll get something that's larger than the expected value, right? But the typical approach of dealing with this, say when this f is finite, when this is a finite set, then what you can do is to enumerate every element of this f, and then use, say, Hofstein's inequality to prove a bound for this, and then apply union bound. You can use basically first use Hofstein's for every single element of this set f, so that you can get a high probability bound for each one of them, and then you can apply the union bound, and that makes the that replaces delta with delta over the cardinality of F. But in the cases when F is finite, this is the right approach to go, right? So in this case, the Hofstad's inequality is to get the pointwise convergence, and the union bound gives us a uniform convergence that allows you to add this supremum in front of this. So the gist of this is that we want this high probability event to hold simultaneously for all the elements inside this F. So that's the reason why it is called uniform. Okay, so what is the corresponding like Hofstad's inequality for this case? And now that we're dealing with something that's slightly slightly more complex. Well, let's take a closer look of this ridge regression estimator that we got. So recall that for every step h, we need to run a ridge regression for each h separately. So the corresponding data set that we get is S is a triplet of SH, I, AHI, and SH plus 1 I, right? So you got this data set for I in 1, 2 to n minus 1. Right, so this is the data that's available to you at the time of decision at episode n, right? And we've seen that the ridge regression solve this optimization problem. S times d sum from 0 to n minus 1. Mu phi s. Right, and again, this is your label. This is your one hot representation of this state in a S dimensional in a S dimensional space where S is a cardinality of the state space, and the closed form solution for this is a sum delta SH plus 1. Yeah, this is something that we've seen just now when describing the algorithm. So I'm just writing it down so we can use it for the subsequent analysis. Okay, so this is a this is a long vector, and this is a d-dimensional vector, and then I'm multiplying with a short d by d. This is 1 by d. This is s by 1, right? And this is a summation of n data points that we observe here, which gives us the ridge regression. Okay, and then this is not really what we want, because ultimately we want to construct this transition kernel, right? So this is, by our definition, is equal to mu hat h of n in the product with S A, right? So this is a probability, a conditional probability given as an A, similarly, by the linear MDP assumption, the actual probability is mu star phi SA, right? So what we're interested in bounding, is for fixed for a fixed v. So this is a function from, or just a vector in the size of the state space. What we're interested to bound is this p hat h minus p h as a inner product with this v, right? So what we want is actually something that's more modest. So this is a scalar, right? So notice that this is a this is a scalar, right? So what we want to construct is a scalar, and by what this mu hat is, we can actually take the inner product of this fixed value function v with every individual one of these this indicator vectors, which essentially selects the particular state and gives us something that's much easier to manage. So this is what we want, and this is equal to phi of s a transpose and summation of I from 1 to n minus 1 so I'm only substituting the closed form solution of this mu into this expression as hi hi. And then after that, you got the dot product with this sh plus 1 I with v with this fixed v, right? And we are subtracting the we can subtracting the mu star with v. And notice that this mu star is the expected value. This mu star is the expected value of this delta s si minus 1, right? So we can group this together by delta minus mu star of sh plus 1 I. This is indexed by this is mu star indexed by shi and ahi multiplied with v, and we can call this error this individual error as h of I, right? So this is a zero mean random variable, and you can see that by what we're doing here, we're trying to construct we're trying to construct a martingale so that later we can apply the concentration inequality sum. Okay, and from the lemma 7.3 of HATS, so this is this is to analyze error of the ridge regression. So we've seen this from we've seen a version of this from the linear bandit lecture. So again, the first term is a term of bias, and the second term is a term that's coming from the variance, right? So you see that this random variable that I just described just now, so this epsilon hi, so these are the difference between the delta delta s h plus 1 I minus the minus its expected value, minus this expected value which is shi ahi, and this is the same as mu h mu h star but I'm choosing this is mu h star multiply with phi of shi ahi, right? So right, yeah, yeah, this is a right this is a right expression. Yeah, actually, I think it is these two things together that is it is these two things together that gives us the yeah, I think I got confused. So let me check, do the dimensionality check. So this is in the order of S by D, right? So in order to get something that's S, then we need to do this. Yeah, I think this is right. So once we plug in this, then we can define this epsilon quantity to be the difference between this one hot representation and its expected value, right? So the second term is zero mean. So what it will give you is a variance, and the first term is a bias, right? So the quantity of interest is in fact only an inner product of this. So we are interested in bounding. No, we're interested in bounding this quantity, which becomes this, and that that requires us to take takes the difference between this mu hat n and mu star, right? So by taking the difference of these two, so the quantity that we're interested to bound is it's not just this, but rather this quantity transpose and multiply with this V matrix, which becomes phi SA transpose mu n minus mu n h in the product with transpose in the product with multiply with V, and then we can group these two. We can group these two together, right? So now we can substitute this bond into this, and it also decomposes into bias and variance, and we can handle the bias and variance part of this expression separately, right? So let's substitute the bias into this. So we'll have the minus lambda phi SA transpose. So the bias part of such inner product that we collapse the dimensionality of S with the a fixed value function V. So this this simply gives us mu h star lambda hn inverse times V, right? So recall that the tricks that we use to bound the bias is by it's by using a Holder's inequality, by splitting this this minus one like this into square root of 2 of n square root of 2. So you will have SA transpose phi h star and lambda n minus 1/2 and n minus 1/2 multiply with V, right? And wait, when I take transpose, this moves to the other side, right? So when I take transpose, this moves to the other side. minus 1 mu n star transpose v. Star transpose v, and we can bound this with lambda and norm of SA under this lambda hn by Cauchy-Schwarz inequality. We can bound this with that, and the other term with inverse as well. And this recovers the exploration bonus, and the second term is lower bounded by the second term is upper bounded by in our previous argument, it's upper bounded by 1 over lambda multiply with a boundedness multiply with the boundedness of this expression, and we get a factor of dimensionality d and square root of d and h. Okay, and these two lambda got canceled out. That's how we deal with bias. And to deal with the variance, and we need to apply this hammer that we learned from the previous lecture called self-normalized martingale concentration bound. And we will see that yeah. So to recall that this is a really nice hammer that allows us to construct a sequence of self-normalizing inequality. So exactly the thing that we need. So this xi will be the phi of si and ai, and this lambda 0 will be the lambda times identity matrix. So this is exactly what we need. And these epsilon i's are these zero mean random variables conditioned on the entire trajectories that we observed so far. So we can apply this to bound the variance part of this ridge regression bound after we take this inner product with V, right? After we collapse the dimension, the dependence on the size of the state space. So we can do that by first checking that this V transpose of this epsilon. So this is a martingale. This is a martingale difference in the sense that we are considering the summation of this, and each individual element, given everything that happened so far, has mean 0, right? Secondly, we need this martingale difference to be bounded with probability 1, and that can be that can be obtained by using the fact that this epsilon is a difference between two probability distributions. Therefore, this is delta minus p of. So this is one hot probability distribution, and this is also a probability distribution. So when you take the difference, the one norm is smaller than 2. And this V function, based on our clipping rule, it is always smaller than h. So we can apply Holder's inequality, and then that gives us a 2h upper bound. So with this martingale difference, we can apply the previous lemma, and that gives us that gives us the required bound for the variance part of the for the variance part of the bound, which simply take this and take inner product with V, right? Take this and then transpose and multiply with V. Okay, so that gives us this self-normalized bound that depends on H. So let me at least talk about the challenge, and we'll have to resume and talk about uniform convergence later. So far we've derived the pointwise convergence. So we've gotten the for a fixed V, right? So we can bound both the bias and variance part of the expression. And in particular, the variance part requires us to use this martingale, self-normalized martingale inequality bound that says that with probability 1 minus delta, then you can bound everything using the horizon dependence h and also the log of the ratio of the determinants. And this is something that you can control from the information. Yeah, so the information gain lemma is applied here as well, as well as in deriving the final regret bound. So all these are the same as in the linear bandits. So once we have this, it remains to solve the problem that we cannot simply apply union bound, because now we have an infinite number of possible value functions, right? And the idea is to go by a so-called covering number argument. So what is a covering number? So let me illustrate this visually. Suppose this is the function class f. So every element inside is a little f, and this f is a mapping from this is a mapping from S to R, or to say it differently, it is R to the power of S cardinality, right? So this is a complicated class, but for now, let's consider this to be a finite dimensional Euclidean class. Let's say that F is a set of all theta such that the theta Euclidean norm is smaller than R, right? So the covering number argument says that like let's try to find the total number of the smallest number of balls with a radius epsilon, such that I can use this ball to completely cover the entire space, right? So these are the little balls. I can do this and then construct a cover and count the number of balls that are needed in order to cover every element. So the reason why it is cover is that for any f inside this function class f, I can construct the f tilde, which is a subset of f, and f tilde has cardinality that is smaller than a number called n epsilon, right? So the covering number is like, so this is what we mean by the covering number. So we want to construct f tilde, which is a discretized version of the set, such that for every f inside this function class, there exists an f tilde inside this discretized set, such that for some distance measure f minus f tilde, f and f tilde, this is smaller than epsilon. Okay, so that's a covering number, and how can we make use of the covering number? So I'm just gonna wave my hand and then say that since we need to bound this p hat minus p times times some v hat, and v hat is and v hat is in f. So the idea is to simply v hat minus some v hat tilde by finding something from the discrete set and then plus and then just add it back. So that's really the key idea. So then this term is something that we can bound using the pointwise convergence argument plus union bound, because now this f tilde is finite, right? And this term we can try to bound by bounding this term with epsilon, by bounding this term with something that depends on the epsilon of this covering number argument, right? So that's a high level idea of how we are gonna proceed with proving the uniform convergence bound, because for every f inside this set there exists something that's close to it that we can use a simpler argument to handle, right? So this is something that we will talk about again and revisit and formalize this uniform convergence argument in the next lecture. All right, yeah, thank you very much for coming, and I'm sorry for running over.